So we are going to look through um over here this particular question about acidities. So this kind of question you should be very comfortable with because a lot of the concepts in acidity and later when we look in basicity as well, they are all about fundamental chem bonding concepts that we have known all the way since J1. So just ignore the background noise a bit, but in this case we should know that the order of acidities is supposed to be alcohol, and then a phenol, then a carboxylic acid. Now notice that this question is 4 marks, right? So whenever you have a 4-mark question, this means that I cannot just state, okay, to state the trend will earn you 1 mark. This will earn you 1 mark, okay? My other 3 marks, where do my other 3 marks come from? Answer, 1 mark is for analysis of this, 1 mark is for analysis of this, and 1 mark is for analysis of this. So a lot of students will just go, oh, I explain why phenol is a stronger acid than ethanol. And then I explain why ethanoic acid is a stronger acid than phenol. And then they think that they've got the marks, but that is not the case. You also need to explain why ethanoic acid is the weakest acid. So why is ethanoic acid the weakest acid? Because ultimately, what is this alkyl group? This alkyl group is electron donating. And ultimately, you cannot say that it is an alkyl group. You need to say that it is a methyl group. Okay, so please always take care to know what exactly the alkyl group is and to be able to state what the electron donating or the electron withdrawing group is. So this applies for electron withdrawing groups as well. You cannot just say, oh, the carbon atom is bonded to an electron withdrawing group or electron withdrawing halogen substituent. You need to say that this is a chloro substituent, a bromo substituent, a bromo-chloro group. You need to be able to state what the group is. Okay, and this electron donating, obviously it is going to intensify. Okay, now sometimes in rough sketching or rough note taking, you might end up writing just this up arrow, but you need to know what word this up arrow translates to. It's not always about increase. In this case, you need to say that it intensifies the negative charge on the O atom in the ethoxide ion. So therefore, the ethoxide ion, which is the conjugate base, is going to be less stable. And therefore, that is why ethanoic acid is the weakest acid. Now, for phenol, let me just flip this phenol over by its side a bit so that I can illustrate better. Now, phenol, if you need a bit of content revision, what makes it a stronger acid than an alcohol? We learned this in hydroxy compounds, right? In a phenol, this O atom obviously has 2 lone pairs, right? 1 lone pair here and 1 lone pair here. And these lone pairs are in what orbital? Is a p orbital. Now, each of these 6 carbons in the benzene ring, what do these 6 carbons have? Or rather, what is the hybridization state of each of these 6 carbons? All of them are actually sp2 hybridized. So as a result, sp2 hybridization, we learned from chem bonding last year that sp2 hybridized carbon has 1 unhybridized p orbital. So all the orbitals that I have drawn here in green are all unhybridized p orbitals. So you will get delocalization. Okay, just to emphasize one more time, this is just a rough sketch. Resonance structures are not in your syllabus for H2, so please do not treat this as a guide on how to draw resonance structures. Okay, so in a phenol, it's a stronger acid as compared to an alcohol like ethanol because the negative charge on the oxygen atom in the phenoxide ion, you need to state what the conjugate base is. This one is ethoxide, this one is phenoxide. So the negative charge on this anion is delocalized. Delocalized into the benzene ring or the phenol ring. Usually I prefer to write phenol because it's shorter, but I guess most of the time the more exam correct term is benzene ring lah. They seem to prefer that somehow. And therefore, delocalize means that the negative charge is, instead of intensifies, it's dispersed. And so, therefore, the phenoxide ion is stabilized. Okay, so this is the general flow of thought. Okay, you need to think about where the negative charge goes, and therefore is my negative charge on the conjugate base on the anion a lot or very little. And remember, the negative charge is borne by this O atom, this oxygen atom in the conjugate base. Okay, and you always need to relate acid strength to the stability of the conjugate base, the stability of the anion. All right, now last one, ethanoic acid. This one, obviously, we know, we just finished topic 18 on carboxylic acids and derivatives. We should know this. I think let me just draw the structure differently, okay? Maybe this will allow it to be better. Now, once again, very similar. There is also delocalization. So this carbon, what hybridization state is this? Once again, it's sp2. And obviously, these two oxygens, they have p orbitals. So there is delocalization like that. There is delocalization like that. So the negative charge is also delocalized, but the delocalization, okay, is, you can either phrase it, I think the way that the notes phrase it is delocalized over two highly electronegative oxygen atoms, meaning this oxygen and this oxygen. But the way I prefer to write it is the delocalization of the negative charge into the C double bond O bond. Because this is a phrasing that we'll be using to compare basicity later in amides. So as a result, this delocalization will cause the negative charge to be dispersed and the carboxylate ion to be stabilized. But why is it that the carboxylate ion is stabilized to a greater extent than the phenoxide ion? Now, this is because your C double O bond has a highly electronegative O atom, and this O atom, or rather the two O atoms, I think this is why the notes prefer to have that phrasing, so that it's more concise. You don't need to repeat the same idea twice. So anyway, because it's delocalized across two highly electronegative oxygen atoms over the CO bond or the OCO framework, these highly electronegative atoms actually bear the charge better as compared to the carbon atoms in the benzene ring. So therefore, this means that my carboxylate ion, which is my conjugate base, ignore the cat, sorry, not sure if you heard that. Anyway, the carboxylate ion is more stabilized as compared to the phenoxide ion. So I think that's it for this question. I will not show you the answers because I've just shown you the outline here. What I'm trying to teach here is the thought process so that you remember. And the exact way that you want to phrase your answers, you can refer to the answer key on your own. So that is it for this question. And I don't think I need to run through part 2 lah, but because it's in the answer key and I think the reasoning is quite intuitive. But basically, just a quick reminder, right? This one, pKa. What's pKa again? Remember from acid-base equilibria is minus log of Ka. Now, ethanoic acid is 4.74. Carbonic acid is 6.35. Now, remember, this is analogous to pH because the symbol P just means minus log. Okay? Sorry, need to... Yeah, now that looks like a G. Anyway, remember pH, stronger acid, or rather higher concentration of H plus is lower pH or higher pH. Lower pH, right? So likewise, higher pKa, because there's this negative sign in front, is flipped. So higher Ka, so stronger acid, higher Ka, lower pKa. So because ethanoic acid has the lower pKa, is a stronger acid as compared to carbonic acid, which is a weaker acid. So because ethanoic acid reacts with NaHCO3, obviously this hydrogen carbonate is going to be, in this case, it acts as a bonded Lowry base. So because ethanoic acid is a stronger acid, it reacts with a Bronsted Lowry base, and obviously acid carbonate reaction, we learned all the way back in Sec 2 that the observation is effervescence of CO2 gas. But you cannot write that as an observation because remember what we've already gone through in your inorganic QA. When you write an observation in inorganic QA, you cannot write effervescence of CO2 because you cannot see that it's CO2 what. So you can only write effervescence of colorless, odorless gas that turns no, sorry about that, that forms a white precipitate in lime water. And also just a note we've just finished a lot of inorganic QA packs. We are very used to writing precipitate as PPT. Okay, throughout the practical paper, you can write PPT and it is understood that you mean precipitate. But this is just for the purposes of the practical paper. Please note that in the theory paper, writing this PPT is unacceptable. Okay, you need to write forms a white precipitate in lime water. So please note this difference in observation when you are writing a qualitative observation in the practical paper as compared to in your theory papers 2 and 3. Okay, I think that should be it for this particular question in the pre-lecture assignment. You can read the the model worded answers that have been uploaded in the Google site if you need further checking of the way that you will phrase your answers. Okay, thank you very much.